Hello and welcome to our presentation. We are Team Hashbash, and today we're presenting our thread-safe Hashmap. I'm Tyler Hostler-Mathis, and today I'm presenting alongside Ashley Vogelweed, Chris Herrera, and David Flores.
We're going to start off with a quick introduction. So a hash map is one of the most frequently used data structures that uses a hash function to map a set of keys and values. It supports very fast updates and queries with an average time complexity of order 1. The standard hash maps used in software development today are designed to be sequential, so this brought up the question, can we make it faster through safe parallelization? Let's talk structure. So before we go into any details, we need to nail down how we define a concurrent hash map. Then, once we have our definition locked in, we'll move to our current accepted research in the field. And then, we'll move into our specific implementation and cover everything from usage to benchmark tests. And then finally, we'll wrap things up with our future plans and improvements for our project. Let's start with our definition of a concurrent hash map. Our development of a concurrent hash map is primarily focused around these three properties: simple, extensible, and correct. So for simple, we wanted to create an API that is easy to use for developers and supports idiomatic method calls from multiple threads. For extensible, we wanted to leave room for improvement on our underlying containers and our data structures. And for correct, we wanted it to be fully linearizable, with each method call having a strict linearization point.
For this slide, we're going to take a look at the research done. What were the experts doing? Before we began development, we needed to form a strong basis for the current work in the field. This ensured that we didn't take any dead-end paths with no true chances of payoff. We also wanted to see if we could find applicability to real-world problems that would benefit from a safe, parallelized hash table. We start with the weight-free hash map research paper. This paper explores a weight-free hash map with atomic operations. This weight-free design avoids deadlock and performance bottlenecks that accompany traditional blocking implementations, such as mutual exclusion locks. The hashmap structure is a multi-level array similar to a tree, and each position contains either a single node or an array of nodes. The experimental results proved the weight-free design to be 7 times faster than the traditional blocking design. Research for this one was conducted by our very own Professor Damian Dechev, Stephen Feldman, and Pierre Laborde at the University of Central Florida. The next paper we took a look at was lock-free parallel dynamic programming paper. This research paper describes the application of a thread-safe parallel hash map being used to solve common dynamic programming problems. It takes a top-down approach, allowing it to solve any type of dynamic problem. This research paper showed a strong use case for a parallel hash map to solve common problems such as knapsack and shortest path. Here, dynamic programming problems are solved using a lock-free shared hash table that randomizes the order in which the subproblems are computed. This paper was written by researchers from the University of Melbourne, Australia, Monash University of Australia, Universidad Politécnica de Madrid, and IMDEA software from Madrid, Spain.
Now that we've defined our hash map and talked about some prior research, let's take a look at our implementation. Our hash map provides a simple and intuitive API, allowing the user to instantiate and query with ease. Here you can see instantiation of a hash map that maps strings to integers, backed by our add-only lock-free linked list, more on that later, with a capacity of 10,007 elements. We then associate the key test with the value 100. Finally, we provide 2 examples of lookup. The get function returns a Boolean generic pair, which can be destructured on call. The Boolean value will be populated with the existence of the key, and the generic with the key's associated value. If the key does not exist, this will call the generic's default constructor. Our hash map provides a templating structure for key, value, container, and hash function. This allows the user to completely configure the behavior down to the underlying container. For an example, if the user would like to use a custom implementation of a thread-safe red-black tree, they could. If they would like to hash a custom type, they must override the STL hash function for that type. As seen in the screenshot to the left, our hash map simply makes calls out to the underlying container, and thus its correctness is directly defined by that of its containers. All of our provided containers have clearly defined linearization points and thus are linearizable. It follows that our hash map is also linearizable.
Here we have a summary of benchmark tests between our hash map and STL on various thread counts ranging from 1 to 20. So STL, which is the C++ standard library, is represented by the pink dotted line on the graph. And here you can see that smaller capacities suffer on smaller thread counts, but they begin to excel with larger thread counts. And large capacities actually beat STL right off the bat. And this is actually expected since we do not currently implement dynamic sizing. But overall, we saw amazing results with our runtime from our concurrent hash map. And more notably, we see that utilizing 20 threads to insert 1 million elements into a hash map with 50,000 slots runs 8 times faster than the single-threaded STL implementation.
Now that we've gone over the hash map, let's check out the containers that drive it. We focused on linked lists for their simplicity and relevancy to class discussion. Specifically, we focused on 2 implementations, lock-free and blocking. Our lock-free implementation does not currently support deletion, for reasons we will cover shortly. A deletion-aware version is in the works. Most importantly, this implementation is very fast. The blocking implementation utilizes hand-over-hand locking and supports deletion. Unfortunately, this has a negative linear relationship between thread count and runtime because of its heavy use of locks.
We now present benchmark data for our blocking implementation, where we can see terrible performance as thread count increases, spiking at 4,000 milliseconds with 4 threads and 20,000 insertions.
On the contrary, our add-only lock-free implementation scales beautifully with thread count, taking less than 500 milliseconds to insert 20,000 elements with 4 threads.
We'd now like to discuss why deletion is so difficult. Consider the following scenario. We have a linked list with A pointing to B pointing to C, and thread 1 is currently traversing through node B. Thread 2 then removes node B and frees its memory. Thread 1 then attempts to move forward in the list, which triggers a use after free violation. To solve this issue, we explored implementing a rudimentary garbage collection system. There are several implementations out there, but the simplest is certainly reference counting. Each reference keeps a count of how many threads reference it, and we only allow frees when this number is 0.
Although we are happy with the work that we have put forward so far, there's always more to be done. Let's talk about what our next steps look like. Removal. We decided to leave removals out because they significantly slow down the runtime due to the need for markable references, retraversal upon compare and swap failure, and reference counting. We also determined that most use cases do not require removals and rely mainly on insertions and lookups. However, given more time and resources, we do want to implement removals in future iterations of the hash map. Dynamic sizing. For the time we had, dynamic sizing was very complex, but we do hope to implement it eventually. The implementation will have the resizing functionality take priority over all other tasks. Specifically, they will hijack the other threads in order to complete the resizing task. Scalability. In our current benchmark tests, we use 4 threads for our linked list and 8 threads for our thread-safe hash map. If we had more resources, we would like to test on more threads to get a true picture of our scalability to determine if there is potentially a point where parallelization may hinder performance.
And with that, we've reached the end of our presentation. Thank you so much for your time. If you have any questions, comments, or just want to chat about what we did, then please feel free to send an email to any of the emails you see listed below. Again, I'm Tyler Hostler-Mathis, and I worked with Ashley Vogelweed, David Flores, and Chris Herrera.